Hi everyone, welcome back. We're now getting into the next topic of the course. This is discrete probability. We're going to build off of our counting techniques from the previous lectures, and we're going to now look at probability, so in particular discrete probability, and then we'll get into next lecture conditional probability, and then after that random variables, and then we'll look at some applications to round out this section. So let's dive into the first example. Suppose we pick a binary string x of length 6 at random. What is the probability that x has exactly 2 ones in it? So let's collect together some of the information that we have in this problem. So we've got this set S, which is going to be our set of binary strings of length 6. So I'll write those out, B1, B2, all the way up to B6, where those BIs are the digits of our binary string, so that's going to be 0 or 1 for each of those positions. And what else do we have? Well, we have the other set we're interested in is the strings that have exactly 2 ones in it. So these are going to be the set of all elements of S such that x has exactly 2 ones. We know the size of each of these sets. We know that the set of all binary strings of length 6 has size 2 to the power of 6, or 64. We also know that those binary strings of length 6 that have exactly 2 ones, we can find the number of them by just saying, well, for the 6 positions, we're going to choose 2 of them, which will get the digit 1, and then the remaining 4 spots will get zeros. So of those 6 positions, we'll choose 2 to place the ones. And what is that equal to? That's 6 times 5 divided by 2, or in other words, 15. So we know the size of these 2 sets. The picture that we have to sort of go along with this is we've got our set S. This is all our binary strings. Inside there, we've got our set A. These are the strings with exactly 2 ones. So for example, 1, 1, 0, 0, 0, 0, or 0, 1, 0, 1, 0, 0, etc. The ones that are outside of A are those strings that either have less than 2 ones or more than 2 ones. So for example, it could be the string of all zeros, so no ones in it, or you could have 1, 1, 2, 3, etc. Or you could have all ones in there. So there's lots of different choices for the strings that are going to be in S but not in A. Now, what we're interested in doing is picking out of this set S some random string. And I want to know what is the probability, what are the chances that it actually is in A. So suppose we pick a string from S at random. The probability that this string is in A is what? Well, it would be basically how big A is compared to S. And so the ratio of those two gives us that probability. So the probability that we're picking something out of S that actually lives in A, and I'll talk a little bit about this notation in a second, is the size of the set of outcomes that we consider successes, or our desired outcomes, over the set of all possible outcomes. And so this is going to be 15 divided by 64. So there's our probability that if we choose a string at random, that it actually came from the set A. So there's not much new here in the sense that, I mean, you've studied probability before. You've probably been introduced to it in grade school. So there's not much new here. It's just that the objects that we're interested in using in our experiments, so the objects we are selecting from and the objects that we are considering successful selections. Those are the things that are relevant to this course. The actual definition of probability is something I'm sort of building off of your intuition from previous courses. However, having said that, we will go through a formal definition of all of these terms. So let's get some of these terms down. The set S, this is called the sample space. And we can think of this as the set of all possible outcomes. So by possible outcomes, it means I'm doing an experiment. I'm selecting a string. And these are all the possible outcomes that I can get from my selection. And that's typically because I am selecting from this set. So these are the set of all possible outcomes. The ones I'm interested in, so the ones I'm considering successes or my desired outcomes, is this set A, and we call this an event. So S was our sample space, A is an event. And this is the set of considered outcomes. I'll also refer to these, considered outcomes, desired outcomes, successes. Various bits of terminology can get used for this set A. These are the things that we're interested in. So what is the probability that when we select something from S, it actually is an element of A? So these are our desired or considered outcomes. And you can see here what we did to compute the probability was we just took the size of the set of desired outcomes and divided by the size of all possible outcomes. And so that's our basic calculation for probability in this discrete setting, so discrete or finite setting. So let's introduce some of these terms again in a more formal way. So here's all the terms we've just talked about. So S is a set of possible outcomes. It's called the sample space. And we're going to assume, at least initially, that all elements of the sample space have equal likelihood. And that means, in the case of our binary strings, it was equally likely that any of those strings could have been chosen. So they all had a 1 in 64 chance of being chosen. Each element of S, that sample space, is called an outcome. And each subset of S is called an event. And we consider it the set of considered outcomes, or as I referred to it on the previous page, we can call these desired outcomes or successes. We generate an experiment by drawing or picking or choosing or selecting at random an outcome X from S. And the probability that X, that object we selected from S, that outcome we selected, the probability that it actually lives in A is denoted by PR of A. So that's the probability that the outcome was an element of our event A. So we're interested in computing the probability of A. What is it? If each outcome is equally likely, so I've sort of written that at the top and it also appears down here. If each outcome is equally likely and the sample space is finite, then the probability is just computed by the size of the event space over the size of the sample space, or the size of the number of desired outcomes over the size of all possible outcomes. So the fundamental principle here is that to calculate the probability of an event, it requires defining two sets, the sample space and the event space. And if all outcomes are equally likely, we can just calculate it by taking the cardinality of A and dividing by the cardinality of S. So we just need to know two size calculations. And that's where counting comes in. That's where our techniques of counting from the last topic will come into play. It'll help us determine the size of these two sets in order to work out probabilities. So let's have a look at another example. What is the probability that a random binary string of size n starts with two ones? So what we're going to do is we're going to continue much the way we did in our first motivating example. And that is we are going to work out what is the sample space, what is the event space, and then work out the size of each and take their ratio. So our sample space, That's the set of all binary strings of length n. So that's b1, b2, dot, 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 all the way up to bn, such that the bi's are either 0 or 1. What's the size of this set? Well, it's 2 to the n. What's the event space? So that's this set A. It's the set of all binary strings that start 1, 1. So they're going to look like 1, 1, and then we'll have B3 up to Bn. Those can be arbitrary letters or digits, 0 or 1. So in this event space, the first 2 spots are fixed. They're 1, 1. So we only have freedom to choose B2 through Bn. So how many such strings are there? Well, for each of those remaining n minus 2 spots, we have 2 choices for each, so it's 2 to the n minus 2. And so the probability that selecting a string at random is in the event space is equal to the size of A over the size of S, or 2 to the n minus 2 over 2 to the n, or in other words, 1 over 2 squared, or 1/4. So if you wanted to express this as a percent, the probability of A is 1/4 or 25%. So there's a 25% chance, or a 1 in 4 chance, that if you select a binary string at random, it's going to start 1, 1. What is the probability that the sum of 2 rolls of a dice is 7? So let's work that one out. Again, we're going to consider a sample space. And we'll consider the event space. And then we'll have to figure out the size of each. What's our sample space? So that's our experiment is rolling 2 die and looking at their sum. So the sum is going to be considered when we talk about the event. But the sample space, that is rolling 2 die. So that would be, for example, the first die could be 1, the second die could be 1. So those are the values of the side that's face up when you roll them. Or you could have a 1 and then a 2, or a 1 and a 3, or a 1 and a 4, or a 1 and a 5, or a 1 and a 6. Or the first die could have been 2, and so you get 2, 1, or 2, 2, or and so on. So we can indicate this by saying our sample space, maybe I'll just move the word event down a bit because I'm going to fill in a little bit more. Our sample space is going to be the set of all pairs. We'll say D1, D2, such that D1 is the value on the first die. And so that could be 1, 2, 3, 4, 5, or 6. And D2 is also a value between 1 and 6. So I'm going to move this over a little bit and just say D1 or D2 are going to be values in there. And so how big is this set? Well, the size of S, there's 6 choices for the first value, 6 choices for the second, so it would be 6 times 6, or 36 possible outcomes here of rolling 2 die. What is our event? Our event is rolling 2 die and getting a 7. So it's going to be the set of all pairs in S such that the sum is equal to 7. So how many are there? Well, there'd be, we'd get 1 and 6, for example, or 2 and 5, or 3 and 4, or a 4 and a 3, or a 5 and a 2, or we could get a 6 and a 1. So there are 6 possible ways that we could roll a 7. And so therefore we can now work out the probability. The probability of rolling a 7 when you roll 2 dice is the size of the event space over the size of the sample space. That's 6 over 36, or 1 over 6. So there's the probability of rolling a 7. Now we could work out other values too. What's the probability of rolling a 6? What's the probability of rolling an 8? Etc. And so you can work out these values. So what are some properties that a probability has? Well, it turns out that there's 3 main properties, and we call them the axioms of probability. And they are as follows. If S is a sample space and A and B are subsets of S, so A and B are events, then the probability of A occurring is a value between 0 and 1. The probability that S occurs, well, if you think about it, it's really saying if I draw or pick from S, what's the probability that what I picked is in S? Well, it's a certainty. It's a 100% chance that it's going to be in S if you've chosen from S. And so that's the probability of S is 1. You can think of that in terms of our calculation. It's just the size of S over the size of S. And the third property is that if A and B are disjoint events, then the probability that the outcome you've selected is either in A or it's in B is the sum of the probability of A plus the probability of B. So these axioms actually hold regardless of whether the outcomes of S are equally likely or not. So in our examples that we've just worked out, all outcomes were equally likely, but it turns out that these axioms even hold in the case when the outcomes are not equally likely. In fact, that's why we're calling them the axioms of probability, because they are the building blocks for probability. These are the basic assumptions we have about a probability function. So from these axioms, we can start to prove results about probabilities. So the first result we'll prove is the rule of complement. This says that if the complement of event A, which is defined there as S take away A, then the probability of the outcome being in the complement is just 1 minus the probability of it being in the event space A. We can see why this will be the case. So the first thing we note is that S is equal to A union its complement, and the intersection of A and its complement is empty. And so these two facts, together with axiom 3 up above, tell us that the probability of S is equal to, maybe I'll put a little 3 up here, by axiom 3, it's the probability of A plus the probability of the complement of A. And that's because S was the union of those two. So I use axiom 3 to get this result. But we also have from axiom 2 that the probability of S is 1. And so we can solve this equation for the probability of the complement, and that is 1 minus the probability of A. And so there we go, a little box to indicate the end of our proof. And so from these axioms, we can start to prove results about probabilities. Here's another illustration of the third axiom. In this case, we're not going to assume or use the third axiom. We're just going to use counting techniques to work out the probability, but we'll see how we could have got the same result using the third axiom. So this is an illustration of why the third axiom is true. What is the probability that a random binary string of size n has exactly 2 ones or exactly 3 ones? So we'll start with our sample space. Our sample space is going to be the set of binary strings of length n. So that's where bi is in 0 or 1. And we have that the size of that sample space is 2 to the n. Now for events, we have 2 of them. So we'll let A be the first event where the string has exactly 2 ones. So it's the set of x in S such that x has exactly 2 ones. And event B is going to be the set of all strings where x has exactly 3 ones. And what do we know about these sets? Well, the size of the event space A, so the size of set A, set of all strings of length n with exactly, or binary strings of length n with exactly 2 ones, is just n choose 2. And the size of event B is n choose 3. So what is the event we're actually interested in? Well, we want the event where it has exactly 2 ones or exactly 3 ones. So we're interested in the event A union B. And so this is the set of all x in S such that x has exactly 2 or 3 ones. How big is that set? How big is A union B? Well, because A and B are disjoint, then this is just the sum of the sizes of those individual sets. And so this is n choose 2 plus n choose 3. And so now we can work out the probability. The probability of event A union B is equal to the size of A union B over the size of S, which is the size of A plus the size of B all over the size of S, which is n choose 2 plus n choose 3 all over 2 to the n. And so there's our probability that the string we chose has exactly 2 ones or exactly 3 ones. Now I said I was going to make the connection with the third axiom, and so that we'll do here. We just notice that this is equal to the size of A over the size of S plus the size of B over the size of S. And that's the probability of A plus the probability of B. And therefore, this is equal to that, and that's what axiom 3 was telling us. So here we've just verified axiom 3 is true for this particular case, and that's why it's taken as an axiom. It's actually true in general, and so we could use it. So we could use axiom 3 here. So we could have used axiom 3 instead of just using the definition of the probability as the size of the event space over the size of the sample space. So we could have used axiom 3, and that would have said the probability of their union is equal to the probability of A plus the probability of B. The probability of A is n choose 2 over 2 to the n. The probability of B is n choose 3 over 2 to the n. And we would get the same result. So from this point forward, you're free to use axiom 3 if you want to find the probability of the union of 2 events which are disjoint, which do not contain any outcomes in common. Let's have a look at another example. In this example, we let the sample space S be the integers from 1 to 12. And we want to know if x is chosen from S at random, what's the probability that x is divisible by 2 or 3? So we have our sample space. That's 1 to 12. And so the size of it is 12. We have our events, and I'll put events in plural because I see an or there, so I see that we are interested in those choices for which they are divisible by 2 or 3. So I'll look at the event A, which is the set of all those n in S such that n is divisible by 2. And so what are those? Those are going to be the numbers 2, 4, 6, 8, 10, and 12. So I can see that there's 6 of those. Could we have done this without actually exhaustively listing? Yeah, absolutely. We can notice that 12 is 2 times 6. So 2 times I, where I goes from 1 to 6, are going to form our set A. And so since I can take on any value from 1 to 6, there must be 6 of them. What about B? Well, B is our event, n, in S, such that n is divisible by 3. So we could list them out, or we could think, what would be the multiples of 3 that go up to 12, where there's 3 times 1, 3 times 2, all the way up to 3 times 4. So there'll be 4 such numbers. So I already know in advance there are 4 such numbers. I don't even need to write down this next step because all I'm interested in the size, but that's fine. I'll write down the next step. It's 3, 6, 9, and 12. So B is equal to 4. We're ultimately interested in the event A union B. So what is that? And let's pause for a second and not fall into the trap of thinking it's going to be 6 plus 4, which is 10, because these events A and B, they actually contain some numbers in common. They contain a 6 in common, they contain a 12 in common. So they contain 2 numbers in common. So how many numbers are there in this sum? Well, there's 2, 3, 4, 6, 8, 9, 10, and 12. So the size of A union B is equal to 1, 2, 3, 4, 5, 6, 7, 8. Now, sometimes it's best to visualize this as a diagram. In this case, we're going to look at it as a Venn diagram. So here's our set S. We have our, let's say, our event A. And then we have our event B. A consisted of the numbers 2, 4, 6, 8, 10, 12. So we had a 2, a 4, a 6 also occurs in B. And then an 8, a 10, and 12, which also occurs in B. And then B had 3, 6, 9, and 12. And so there is our picture. The other numbers, we can write them down. We've got a 1, 2 is used, 3 is used, 4 is used. We've got a 5, 6 is used. We've got a 7, 8 is used, 9 is used, 10 is used, and then an 11 out there. So there's all our numbers from 1 to 12 separated amongst the various events. How can we have obtained the size of A union B without having to exhaustively list them? Well, we can notice that A union B, the size of it is the size of A plus the size of B. But when we do that sum, we actually count anything that's in common between those two sets, namely the 6 and the 12. We've counted it twice. So this counts the intersection of A and B twice. Anything in there, it counts it twice. So what we need to do is we need to subtract off one count for each of those elements. So in this case, it is, A is 6 plus B is 4 minus the intersection, which was 2. That gives us our value of 8. So that's another way to do this count without actually having to exhaustively list them. Now you may say, well, you had to list them because you drew your diagram with that. But if you think about it, we could have worked out each of these values, the size of A, the size of B, and the size of intersection without actually having to list them as well. Because the intersection would just be all those things divisible by 6, and 12 is 2 times 6, so there'd be 2 things in the intersection. So now we're all set. We can work out the probability. The probability of A union B is equal to the size of A union B all over the size of S. And we've worked out those values. That was 8 over 12, or in other words, 2/3. Now I'm going to make one more connection here, and that is to write out that first step, this thing here, as this expression. If I write it out as that expression here, I get that the numerator is the size of A plus the size of B minus the size of the intersection all over the size of S. And then I can divide S into each of those three parts, and I get the size of A over the size of S plus the size of B over the size of S minus the size of the intersection over the size of S. And what are those? Well, the first one is the probability of A. So I got the probability of A. And then the second one is the probability of B. So that's added to the probability of B. And now I'm going to move this over a little bit so we can not have to squeeze it all into that bottom corner. So I'll do a little bit of reformatting here. There we go. And what is that last expression? Well, that's the minus the probability of A intersect B. And so what we have is that the probability of the union, in this case, A and B weren't disjoint. So I couldn't just say it was the probability of A plus the probability of B. In other words, I couldn't use axiom 3 here. Axiom 3 requires the two events to be disjoint. In this case, they aren't disjoint. So I couldn't just say this probability was the sum of the two probabilities, but what I've in fact now been able to discover is that it's the probability of A plus B minus the probability of A intersect B. So the probability of the events A and B occurring. Because those things essentially were counted twice when we looked at the probability of A plus the probability of B. And this gives rise to what we call the additive rule. So if S is a sample space and A and B form two events, then the more general form of axiom 3, which applies in the case where A and B are not disjoint, is that the probability of their union is the sum of their probabilities minus the probability of the intersection. So let's prove the additive rule now. So how are we going to prove this? We will prove this from the axioms. And so how are we going to set this up? Well, I'm going to have a picture in the back of my mind that I'm going to use. I've got my event A, got my event B, got our sample space S. And we're just going to notice a few things about this diagram. So we're going to notice that, 1, A union B. Okay, the problem is they're not necessarily disjoint. But can I write this union as the union of two disjoint sets? And the idea is, absolutely I can. What I can do is I can look at A intersect the complement of B. Okay, so what is that? In our picture, A intersect the complement of B, that's all this stuff here. It's anything that's in A but not in B. So that's all that stuff. And therefore I can see that A union B is that stuff union with this stuff. Well, that's just B. So what I have is that this is true. A union B can be written as A intersect B complement union B, and I notice that this is now a union of disjoint sets where A intersect B complement intersect B is the empty set. So those are disjoint sets. What else can I do? Well, I'm going to look at the set A for a second. And now for my set A, I'm going to notice that this set A can be written as A intersect B complement again. So this set here. Union this stuff. And that's A intersect B. So I have that A can be written as A intersect B complement union A intersect B. And again, that's a disjoint union. So where A intersect B complement is disjoint from A intersect B. And so I've got these two equalities. And the nice thing about these two equalities, if we look to see what's involved in it, there's a union of A and B, there's a B, there's an A, and there's an intersection of A and B. Those are all of the ingredients we need in this equation. The only thing we don't need is this A intersect B complement. And so that's what we're going to do. We're going to take these two equations, we're going to combine them together and get rid of the A intersect B complement. But we're not going to do it on these equations. These are equations involving sets. We're going to do it on equations involving probabilities. So what we can do is now take probabilities. Take probabilities of 1 and 2. So the probability of A union B, so this is equation 1, is equal to the probability of A intersect B complement plus the probability of B. And that's by axiom 3. Because those sets are disjoint. And the probability of the union is just the sum of the probabilities. And doing the same thing with the next equation, the probability of A is equal to the probability of A intersect B complement plus the probability of A intersect B. Again by axiom 3. And now what can I do? Well, at this stage, we are in pretty good shape because we've got two equations. These are just numbers in these equations. So I can get rid of this expression. So I can notice that this now is equal to the probability of A minus the probability of A intersect B. Right? I just solved the equation for the probability of A intersect B complement. And then we use this to plug into the previous equation. And what does that become? That becomes the probability of A union B is equal to the probability of A minus the probability of A intersect B. So that's replacing that first piece. So that piece here, I've just replaced it with what the expression is by using the second equation. And then we've got plus the probability of B on the end. And that's exactly what we wanted to show. It's the probability of A plus the probability of B minus the probability of A intersect B. And there we go. We've proven the additive rule. So this is a much more general version of axiom 3. This additive rule now allows us to compute the probability of the union of two events regardless of whether they are disjoint or not. If we think about this, we can now go back to that previous example and we could do it in the following way. So we're going to revisit it. We've got events A, B, and A union B. And what this tells us is that if we wanted to know what is the probability of A, we know that that's going to be 6 over 12. What's the probability of event B? So the number is divisible by 3. That is 4 over 12. What's the probability of the intersection? That's one we haven't worked out, but we can. We can say A intersect B. What's the size of it? Well, A intersect B is the set of all integers divisible by both 2 and 3. So those have to be the integers divisible by 6. There's two of those, 6 and 12. And so that means that the probability of A intersect B is 2 over 12. And now our additive rule, the one we just proved on the next page, it works in this case because we can then say, well, what's the probability of A union B? this is equal to the probability of A plus the probability of B minus the probability of their intersection. And so that's going to be 6/12 plus 4/12 minus 2/12, or 8/12. And so that's an illustration of the additive rule in this particular case. We didn't use the additive rule when we first did this. We just counted the size of these sets. But we could use the additive rule in this case now. The next exercise has you generalize that particular example. In this case, now we've got 3 conditions. We want it to be divisible by 2 or 3 or 5. So that requires us to consider 3 events, A, B, and C. The event that is divisible by 2, the event that is divisible by 3, and the event that it's divisible by 5. And so I'm going to leave you this exercise to ponder about generalizing our previous exercise where we just had 2 and 3. And see if you can work out a generalized version of the additive rule that works for 3 subsets. All right, that's it for this lecture. Thanks for watching, and we'll see you again next time.